Vamos a comenzar. Screen. Esto. Annotate. Spotlight. Okay. We'll start now to talk about stability, finally. After seeing all the detail around when there is equilibrium in stars, the equation for the equilibrium, the equation for every properties of the stars, equation of state, nuclear reaction, then looking all together to see how can put to have some mathematical model to describe all the properties. Now it's the turn to see how to determine when a star is in stability. There are, as you know, there are several ways to have stability. The classical examples are the position of the ball with some with energy, potential energy, kinetic energy. If a ball is atop of a hill, can be still, but is in not stable equilibrium because a mole shift in a direction on another will fall the ball toward one direction or another. In this case, for a star, that means we have a situation where the stability is not stable and the star can suddenly start to collapse or start to expand indefinitely or up to the. The other is the typical, the ball in a valley that is stable because a small change in one direction or in the other, the ball just will go back and to the original. In this case, this perfect will be started to oscillate. In fact, we can have the equilibrium, the ball there doesn't move, and with the small movement, vibration continue to stay there because are too small to start to oscillate. Instead, in the top of the hill, the small variation will start a big movement. But also you can have another kind of stability when the ball will start to move and the ball start oscillate from position to another without going too far, but always moving in this way. And the physical situation, for example, is a pulsating star. Pulsating star is not obviously in equilibrium, but is maintain the oscillation inside a certain range and doesn't go in a complete collapse and complete expansion. Continuously oscillate is a periodic movement. In the case that there is some dispersion, there's a loss of energy during this movement, the oscillation will be damped and go to zero. So we will have going back to the more stable situation with the ball fixed in a certain position. There could be also the opposite, that even if it's in a situation of stability, but the oscillation are not damped but are increased, and then will start the situation to oscillate up to a certain value that disrupt the situation. These are also because there are some instability that cause in the astrographic giant branch that starts to have certain oscillation that result at the end to the expulsion of the envelope and the creation of a planetary nebula. Stars have all of the kind of stability as we see during stellar evolution. The main is what stability is the classical main stars, main sequence stars, more or less, because not all the main sequence stars are so perfectly stable. We see that is called the secular thermal stability. Secular is that means that happen in long scale, is a stability on long scale. It means that permit a stability that stay for a long time. In fact, usually it's classical for the main sequence stars. As we saw essentially at the beginning, the total energy of the stars is the potential energy that is, in this case, usually is always indicated as negative because it's zero at the infinite far away for particle when the stars is completely dispersed up to the infinity, and up to the concentrated in one point that is like minus infinity. The internal energy that is strictly positive, neither zero, because you cannot have you cannot go to the zero, absolute zero, plus the macroscopic kinetic energy, but as we saw at the beginning, this is really small in general for instability. Will be not zero, is not negligible when we are considering star, but not we are considering this case just a normal star in the static equilibrium. So in this case, the macroscopic kinetic energy is definitely smaller than the other two, so can be negligible. This is actually in absolute value, because since this is omega potential potential is negative, negatively minus infinity, an energy that is minus infinity, will be okay, but okay, internal energy is positive, so we understand. For the VR term, we know there is this relation between a term that is connected with internal energy and the potential energy. And we have the relation with the pressure divided the density with the internal energy by unit mass. That give us the usual relation that depends on the situation, on the equation state, for among the total internal energy and the potential energy of the stars. For the ideal gas, considering so the pressure, total pressure is almost all the pressure of the gas pressure. So beta is more or less 1. We have the classical internal energy, it's equal in 1/2 of the potential energy. So the total energy is the sum of the two. Since 1 is 1/2, you have 1/2 of the potential energy as is value, or minus the internal energy of the gas, obviously, because we have to just consider gas, that is less than 0. Total energy in stars have to be less than 0, otherwise it will be not gravitational bound. So this also makes sense since the internal energy have to be positive. If you consider the ideal gas, but there is radiation, something radiation, so we have not just consider just throw away. We have the relation among pressure and density is 2/3 of the internal energy of the gas and 1/3 of the internal energy per unit mass of the radiation. That gives us so relation is not more as here that the total internal energy of the gas, that it is the energy of the gas that is almost the total energy of the stars, that is minus 1/2 of potential energy, but we have the twice the internal energy of the gas plus internal energy by the radiation is equal to minus the potential energy. So we can rewrite it everything as the internal energy of the gas is equal to minus the sum among the potential energy and internal energy of the radiation divided by 2. And we similarly, since the sum, total energy is the sum of the internal energy of the gas, of the radiation, and the potential energy, we have this value, value 1/2 of this one, that is, as we saw, minus internal energy of the gas, and then minus 0. Essentially similar to the other. What changed? That we can see that actually we can consider that the internal energy due to the radiation can be seen like a reduction of the gravitational attraction. That's because the radiation produces not the gravitational pressure that expand like the gas, but have not mass. Technically, as general relativity, light has a mass, but is really small. As we saw in all its life in the main sequence, the sun will just lose 0.1% of its mass. It is in all 10 to the 10 years. So during a certain moment, the weight of the radiation is completely negligible, so doesn't contribute to the potential energy. So we can see the change in the potential energy as 1 minus is absolute values minus the energy of radiation, and call it as an effective gravitational potential energy. That is the potential energy corrected by the effect of the radiation. As I remember, every number can be seen as the multiplication among its sign and its absolute value. So we know, as I said, that the potential energy is negative by definition, because the integral is going to be negative plus a constant, and we decide to be 0 because we consider the potential energy when the stars are completely expanded up to infinity 0. So it can be better written this way. So we can take away 1 minus here, this come minus, and have as absolute value. So we can see that radiation, the effect can be seen. It's not exactly can reduce the potential energy, but it's similar. It can be like use a reduced potential energy, what we call ineffective. So even if we consider that the gas pressure is completely dominant as a pressure, total pressure is given only by the gas, or if both, we have the same situation that if the absolute value of this effective equation potential, that is in the case of only gas, is just potential. If this increase in absolute value, that means that this value decrease because it goes more negative. So there is a compression. The internal energy increase, the internal energy of the gas increase, and the temperature will increase. That causes also internal energy of the radiation to increase. If the effective potential decrease, then internal energy decrease and the temperature decrease, as we saw before. But now we will see in detail the effect. Because as we saw before from the thermal equation from the thermal equilibrium, the variation in time of the energy is equal to the integrated all the mass of the energy production rate per unit of mass, less the luminosity of the stars, or the luminosity at the radius. So we have this nuclear luminosity, as we call the luminosity produced by nuclear reaction, less the luminosity exiting from the star, the sphere gas. Obviously, if we produce more energy than what is going outside, the internal energy of the star will increase. It's going toward the positive value. And while if luminosity it is escaping is higher than energy produced by nuclear reaction, then there will be and total energy will be more negative. In equilibrium, we have that the two are equal. So if you consider the nuclear luminosity as its value in equilibrium, that essentially is the luminosity, plus in addition, so we have a little increase of the production in energy by nuclear reaction. We'll have that for the reason the energy, total energy will be increased because it's equal to this little amount. But this means that its absolute value will decrease because, as I said before, the energy of the star has to be negative because otherwise it will be not gravitationally bound. It makes sense. Otherwise, that means that internal energy, its value is greater of the bounding by the gravitational effect, and the gas will disperse. Then, consequently, the internal energy of the gas will decrease because, as we saw before, it's just a change the sign, but the absolute value of the two is equal. So the internal, if the total energy in the absolute value decrease, also the internal energy will decrease. That means the temperature will decrease, and also means the total, the absolute value of the potential decrease. It means it will be toward the positive direction. That means the radius will increase, and so that means the average density will decrease. And considering that we know that we can write the energy production rate as a constant multiplied the power of density and temperature. Both are positive. I put also equal to 0 in the case we have some reaction that is not dependent on the two, but usually they are both positive. For example, nuclear reaction for the hydrogen that is classical for main sequence. So in a situation where we have stability in the star, we have lambda is 1, and this one we can take between 3 and 5. Actually, this is for the proton reaction, so something like the sun up to more or less 2 solar masses. Since the temperature, the mean temperature decrease and the mean density decrease, we'll have that epsilon will decrease, and we saw here the nuclear luminosity is connected, so will decrease. We'll take away this value of the increase, and so the nuclear luminosity will go back to the value of the equilibrium. This is because what is called the gravothermal heat capacity of the star is negative. That is what happened here. So the gravothermic, because it's the connection among gravity and the thermal characteristic and thermal energy. When we have the gas will collapse, goes to more negative energy, potential energy, we'll have the volume decrease, actually. The star will start to heat, and the opposite, the star will cool. And this is what permits to the star to be stable for a longer time, because if you have the star, we have a small variation, can be for some reason fluctuation in the production of energy by nuclear reaction, small change in the luminosity, as we saw, the luminosity given by the opacity and the internal gradient of the temperature. So for some reason we have some fluctuation there. The stars can stay, will correct and goes back to the situation. This is essentially what we saw. We have the ball at the bottom of the valley. We have a small variation, a vibration, and the ball just move a little but goes back quickly to the equilibrium position, because he have all the situation will go back to the equilibrium for the stability. And this is classical for the main sequence. In fact, we have like good stability, except for the part that are crossing. We see the instability stripe, where are the pulsating stars, and this is because there is a change in the luminosity, not here, but for several reasons we have problem with due to the ionization that will change the opacity. So a small variation cause to going to follow up to a situation where it's inverted. So we have this kind of pulsation. But let's see the other. So this is the classical stability for the stars. Everything goes well, but we have obviously also some thermal instability. We have some cases where the star can have some problem. Classical, as I already mentioned, is the degenerate gas that are this classical polytropic relation among pressure and density, with the Kn and the coefficient n plus 1 divided by n, with n will be 3.5. I need to redo that. In the case it is not relativistic, and then 3 in the case of relativistic, that means that the value that is actually the adiabatic coefficient is 5/3 one case, 4/3 in the other. The virial is the same. We have always that the total energy is equal to minus the internal energy of the gas. In this case, definitely, because also the radiation in this case is not so strong. Also, because when you have the degenerate gas, usually, for example, is the core of contracting stars, there is no nuclear reaction there, because we have more are is really small, not important. So essentially, we have not the production of energy, so we are not radiation that flowing from inside. Just stay there. There is, but not so strong. And the internal energy of the gas is, in this case, it's not more a function of the temperature, but in a function of just the complete degenerate gas on the Fermi energy that is proportional to the density. And it is why here the pressure doesn't more depend on the temperature. So going back, what happens if okay, nuclear reaction is increased? That will at the beginning, obviously, there is not more, but we see that at the beginning, the degenerate gas have no production or any nuclear energy. But for example, when the star compress, at a certain point, the gas, the core of red giant starts contract to raise the temperature up to the energy, to the temperature start the burning of the helium. And at a certain point, we'll have the start of the nuclear reaction. And this energy will be at a certain point greater than the luminosity that can flow. This means that we'll have the energy, total energy will increase with the time. That means that its value, absolute value, will decrease. That means that the internal energy of the gas will decrease, and so the density. And here is the problem. We have no more a connection with the temperature. Before, this will decrease and the temperature will decrease. Now just the density will decrease. Similarly, and the potential energy in absolute value will decrease. And so going up toward 0. So also, since there is an expansion, the density will decrease. But as we saw previously, the production rate for the helium and everything that above have okay, not small and depend on the density, but definitely bigger the variation with the temperature. The temperature T8, as I'm told, is the temperature in unit of 100 millions of Kelvin. This usually is 1 because 100 million of Kelvin will start the helium burning.
Professor, what was the numerator in the exponent in the temperature there?
Here, 43 divided T8.
Oh yeah, 43.
Okay. You can see in the notes for the nuclear reaction. But this Okay, in this case it's 40, but it's really big. So you can see that in this case, even if the density will decrease, and since we have an increase for the temperature for the nuclear reaction, the increase will be feed more the nuclear reaction. Is the same. So if you are, we start the nuclear reaction again, this we have an increase of the total energy increase in the direction, not in absolute value, but relative value, that will cause actual a small okay, small decrease in causa will cause a decrease in the density, but there is also an increase in temperature, so there is not enough to turn off or regulate to have less and more adequate value. The nuclear reaction of the nuclear reaction temperature increase, so we have an increase of the production, as I said, since the nuclear reaction increase as the engine they produce, this will cause an increase of the temperature and so on. It's true that, remember, temperature is the kinetic energy. It's true that the kinetic energy of the gas, but it's essentially the electron, not depend on the temperature, but only the density. But we have also ions. In this case, it's a little, the contribution of the electron as a fraction is definitely bigger, but there is a mixed, and we have interaction, is what's called opacity, among the photons, the electrons, and the ions. That means that the photons are creating, interact, pass a little energy to both, that will be redistributed, as in the case of the internal energy, so and the temperature. Just to remember, when the nuclear reaction produces the photons, they produce photons on the order of megaelectron volt. When the photons that are present in the sun are emitted of the order of electron volt. It's a change of 1 billion. This change is because of the radiation and the matter interact with each other and thermalize and pass energy one with the other, and that's cause the increase of temperature. This chain of because at the beginning the temperature just increases with the contraction, that is passed directly from potential energy to internal energy. Then start the nuclear reaction. This is the point of view of stellar. We have an ulterior increase, and this called what is called a thermonuclear runaway. The start to produce more and more energy, and in fact, the nuclear reaction, as I said, the generating gas are not an healthy mix, because always when the degenerate gas start a nuclear reaction, never going really well. There can be two kinds, deflagration or detonation. Deflagration is subsonic, so the wave that are burning propagate slowly, detonation propagate really quick. Depending on the situation, we can have, for example, that if the temperature increase enough, it's you can start to rule again the equation of state, so we have not a catastrophic outcome. We are not the explosion, detonation. It is called what is the degenerate lift. Just to remember, perfect degeneracy is only its absolute zero. The other, we can have 90% degeneracy, really high, but it is also. And as we saw, I show you that in partial degeneracy, the actual equation of state is not perfectly not depending on the temperature. Some term they still can depend. This is because in perfect degeneracy, absolute, it's this is the square. It's populated perfectly up to Fermi energy, up one here, then drop to zero. Obviously not, there is always an E, a something, and when we increase the temperature, yes, there is some part of the electron here are pass here. From here to here, because, okay, can be also something here, but quickly the other electron will refill the lower state. So we start to move some part of this one to change the shape up to a situation where it starts to be more similar to the Maxwell-Boltzmann distribution, the exponential. So the degeneracy is not more so strong. That means the equation state start to be similar to the one for the Maxwell-Boltzmann situation. So the degeneracy is lift, and the runaway, thermonuclear runaway will stop, and the star is safe. This is, for example, an example when start the helium burning in degenerate gas. That is what is called the helium flash. That is a real flash inside, but just inside of the stars. Outside, we'll see simply that the stars actually drop in its luminosity, because from a little expanse will go back to a situation more compact. All the energy of this flash, it's used to remove the degeneracy, to leave the degeneracy, and the stars will survive. From the point of view with the polytropes, we can have the known situation, and we have this this value that we can also see from relation with the singular value for the pressure and density. We do the ratio here, and we get a third. In general, we put a more general equation of state, since the polytropes are not governed by specific. We saw that stars in main sequence with a classical gas, ideal gas, can still be seen as a polytrope of index 3. We have this situation, we mixed, and in the end we have the variation in temperature is proportional to variation in density, central density, by this constant. The sign of the variation is just since B is positive, A and B are positive, are connecting this way. So if A is less than 4/3, this is positive. So the variation in temperature, variation in density are connected. That means if the density increase or the radius decrease, the temperature increase, and instead of if the density decrease and the radius increase, expansion, the temperature will decrease. That it was happening, for example, for the ideal gas, and this is exactly what we saw for the before the secular stability. If more energy will expand, and there is a drop in temperature, drop in density, and this will turn down the nuclear reaction. But if you consider the degenerate gas, A is not more less of 4/3, is among 5/3 and 4/3, so is a range that it is above. So the sign in the opposite, and P is not exactly 0. It's more than 1. As I say, that the perfect degeneracy are just in absolute 0. We are always in a state of mixed value. In this case, we have the opposite. We dropped the density, will increase in temperature. That means an increase in nuclear production. This is because, as we said, we have essential production of helium burning, carbonium burning, and so on. Not the hydrogen can be nearby, but anyway, have less dependency on density. In any way, usually we don't have degeneracy in a star that burns hydrogen. Because also the small stars are not in the degenerate state. So it's about nuclear reaction with degenerate gas. We are always talking about helium burning or above. They are strong, really strong dependence with the temperature. The last is the thin shell instability. That is a peculiar situation. We just consider a small thin shell in the star, where its depth here is x, really smaller than the radius, total radius of the stars, among radius R0 and R. For the isomologous relation, we have that the P on P is depend on minus for the variation on the radius. That means if you have in this shell we have a nuclear reaction and we are producing more, we are increasing energy, that the shell will start to expand, pushing the layer that are above, expanding everything, and so decreasing the density and decreasing the pressure, because we are going a little further, and we saw that the pressure is lower outside. The change in the mass here in this small shell, the thin shell, it's okay, classical for P Greek, the the surface here multiplied by how is thin the shell multiplied by the density. This is the volume by the density. That means that the variation in density of the thin shell is proportional to minus delta x divided by x. The variation of the x is the same essentially of the variation of the radius. So we change the delta radius divided by x, and multiplying divided by the radius, we have the variation, relative variation of the density is proportional to the relative variation of the radius multiplying by minus the radius divided by how the shell is thin. See that we have definitely a change. Before, we have the relation among the two relative variation was -3. Now we have the radius divided by how is thin the shell. And this value can change. If you do the same pressure here, or like this one, and go again, we have the same situation. And for the stability, we wanted that for a reduction of the density, so the expansion, we have a decrease in temperature. That means then, since we wanted to follow the sign, this is have to be positive. B already saw that is positive by definition. So A must be less than 4 times the ratio among the how is thin the shell and the radius of the distance from the center. For ideal gas, for example, it is 1, and this can be if wait a moment. Oh yes, if the shell is vast enough, not too thin, or for example, it's is 1/3 of the radius. We have a third. It is bigger than 1, so we have a solution of stability. But we started to decrease this situation. We have it goes really small. Definitely this start to be less, so we have the star also in ideal gas, non-degenerate gas. We have instability. And what happened? We have this situation for the energy, as I remember. Also remember that even if it seems strange, if the nuclear luminosity is less than the total luminosity, so we are losing energy, the total energy will decrease, will be more negative. That means the internal energy of the gas will increase the temperature. This will increase the total nuclear luminosity. That will be back for the variation on the energy will be, the total energy will be 0. So we have stability. This without considering the relation among L and the temperature. This is the relation for stability. If we have considered also that the luminosity depends on the temperature, but as we saw, the relative variation of the luminosity with the temperature is just 4, while for the nuclear luminosity is proportional with the coefficient that is nu, that is not usually definitely bigger than 4 for several, except for the proton-proton, but for CNO is around above 15, 20 several value. For helium burning is 40, more or less, a little less, but anyway, always bigger than 4. That means that even if the total, the increase of temperature will goes to increase the nuclear luminosity and also little, also the luminosity, the increase of the nuclear luminosity will be definitely bigger than the luminosity. So even if there is more loss, so the energy, total energy will increase in absolute value because decrease is more negative, and that will cause an increase in temperature. Then anyway, the nuclear reaction will manage to balance and stop this variation. This shell instability is actually a situation that we'll see. This classical, as we saw, is especially when we have strong dependence with the temperature of nuclear reaction that depends strongly with the nuclear reaction, that are CNO or the helium burning. And this is the case essentially when we'll have stars that start to contracting after we finish to burn the helium in the core. We have obviously stars, for example, after the main sequence, we'll see the star will stop to burn in the core, the helium, and start to contract. But remember, the nuclear reaction depends essentially on two things: the temperature and the density, and the composition. In the center, they are stopping the nuclear reaction burning and hydrogen burning simply because we have not enough hydrogen. Or there is completely depleted, or there are too few to produce something. So they start to contract, increase the temperature. The temperature never goes down. That means that with the increase of the temperature in the center, obviously we have a situation with 10, 15 million degrees outside the core. So we'll have an area where the hydrogen will start to burn outside the core, so in a shell. After the hydrogen, the helium also is completely depleted in the center, more or less. We'll have two shells, one the burn more external, the burn hydrogen, and one among this shell and the core that will burn helium. And this shell, as we will show, it's really, really, really well dependent on the temperature. And exactly what we have here is really well dependent on the temperature. So it's if the temperature is too low, doesn't work. And when it started to increase, it's really quick to produce. So quickly, if your temperature really high, will the helium will be completely depleted. So the shell for the helium burning is a thin shell. And we'll see this exactly this kind of stability. In asymptotic giant branch, we have this shell that we start to have sometimes an increase that will cause a runaway with over expansion up to because the stars to expand a little, and with an increase of the external convection and so on, several effects. And so one of the effects is the throwing part of the envelope outside, because it's pushing this increase of the luminosity, some part of the small amount of gas that remains. And I'll stop here. Because I didn't want to. Come on. Okay. Do you have any question?
I do.
Yeah.
On the
pause, because it's I don't want to start everything, because essentially two parts: stability and dynamic instability. I want to do it separate. What's your doubt?
I have a question on the thin shell stability. I'll show you where. Do you see my mouse?
No, I cannot see you because
well,
I'm sharing. So I
can write on your screen.
You see, I think that I didn't see
it. Do you see?
No, I see it. I see it. Sorry, I see it.
Yeah. That's the rate between the wide of
how is thin the shell.
And the position from the center. Does that mean that this is different if the shell we take is closer to the center of the star? Or that's just the radius of the star?
Yeah, it's for a shell that is really near, R is small, so this started to increase, so more stable. As soon as the shell starts to be thin or far away, they start instability. This is also probably because you see this instability not so much on the red giant branch, while you see really well in the asymptotic giant branch, where you have the core that stay more or less the same size, and you have the two shell more far away, and also the helium burning shell is definitely smaller, so it's easier to see the situation.
And how do we make the jump from analyzing a thin shell to a whole star? How do we extrapolate the results from one shell to a whole star?
No, this is valid just for the thin shell. It's not the stability of the star. We have that if you have a nuclear reaction released just in a small thin shell of the star, okay, we can have an instability similar to the one for the we have, for example, in the center of the core degenerate gas. That is an increase. It's quite similar. It's just that before was for third. Here it's a change, but it's just not the stability of the whole star. Before we saw, for example, the stability, the secular stability is for the star in general. The thermal instability for degenerate gas is for the degenerate gas we use just the core, not outside, obviously, because even if sometimes it's most of the mass stay in the degenerate core. Here is just considering other, in fact, is an instability that was discovered later. That what happened, I think, to explain what is observing with asymptotic giant branch stars. If you have the nuclear reaction yeah, working in a small thin shell around the core, or
Oh,
a
so
thin shell in general.
you can have nuclear reactions outside the core on a
Yeah,
shell.
outside. This means that this shell suddenly will start to produce a lot of, will have a runaway, thermonuclear runaway, will start to produce a lot of energy and will not stop quickly.
I
In
have
all
to.
the other situation, we saw this instability, it started to increase and then it's quenched
So when you
really
say
quickly.
the
Here, it started to produce a lot of energy and cause the start of the consumption to react in this whole situation. Also because these shell are just above the core, so all the envelope are affected.
okay, when you say the nuclear luminosity here, you refer to the nuclear luminosity of the shell of the or the nuclear luminosity on the core.
In this case, when it's applied, the nuclear luminosity of the core is zero because it's not producing no, in some cases producing, but in this case, for example, asymptotic giant branch are not more producing a lot nuclear reaction. But is for the shell that is supposed is the one that is producing the energy in general. Because above the shell there is no more nuclear reaction. It's a simple situation, and just thinking that the nuclear reactions are in this thin shell localized in a certain point of the star. This is the general situation. Then I also give you a real situation like the shell instability of the helium burning. We will observe the effect in a symptomatic giant.
It would be of help if we could see to which case this criteria applies. I mean, to what kind of star or what phase of the evolution of stars.
As I say, this thin stability is observed in the symptotic giant branch. So in the stars, we have the main sequence that where the essential main sequence is defined perfectly in this way. It's a star where the main energy production is given by the helium burning and the happen in the center, in the core. This is the
Okay.
definition of main sequence stars. When a star is producing is burning the helium in the core, is the main sequence, and also when this energy production is the main source. Can be a little contraction, but because
What
essentially the
what
star is
stars?
always contracting.
What stars?
Then we'll try to increase energy in the core to burn the helium. That is a giant branch. Horizontal branch is where it's burning the helium. And then goes back toward in a asymptotic way to the red giant branch, in the asymptotic giant branch. And there are the stars that are burning the helium and the hydrogen in shell with the core of carbon and oxygen. Usually it happens here. The main effect are here. Then you can have all this instability in all the situation where you have a shell burning in nuclear reaction, easily depending on the temperature. But after that, you have the burning of the helium. We start the burning of the other. Everything's are easily quick, so it's not so you can notice really well as in the asymptotic giant branch. The thin shell instability usually is mainly noticed in the first asymptotic giant branch. When there are instability, the famous the first, the second dry up that are mixed from convection that goes from the envelope up to the burning shell and mixing everything. This is also the reason why asymptotic giant branch stars have a chemistry that are really well different from the giant star. And so you look in the chemistry, you can detect which one are which. It is also the reason why you don't want to pick asymptotic giant branch stars when you are studying the chemistry of globular, because its chemistry is completely rearranged. And
what would be the difference between the chemistry on asymptotic giant branch and the red giants?
essentially, since we see in the detail, but these drop are taking to the surface all the result from the burning in the, for example, of the CNO, and all the reaction they are working at the similar temperature of the CNO, that are the neon sodium and magnesium aluminum. It is the reason why in the atmospheres and they are changing in the ratio of this element, and when for the final, for this kind of thin shell instability, the envelope will be thrown completely away and dispersed as planetary nebula. All this gas, for example, we see with the second population in globular cluster, this gas goes to contaminate, to pollute the gas of the stars, the less massive stars. They are still contracting, still forming, and for this reason, we'll have a change in their chemistry. And we'll see that, for example, the famous anti-correlation of in oxygen sodium. This is because the CNO are depleting the oxygen, while the parallel process will increase the sodium, or the change in magnesium aluminum, because here there is just one reaction that reduce one value to increase the other, and so on. We can also have something that just arrive to the shell of the helium burning, some change in some of the other elements. Essentially are these main values.
Okay.
Before, there is a little mixed in the red giant branch, but doesn't change a lot. There is a convection that causes the red bump. It start stay.
I remember
because on the convective area are bringing more hydrogen to the hydrogen shell, burning shell, so stop a little to expand. But then mainly the main mixed on the surface. So there is the reason why we are looking for red giant stars of the red giant branch for the composition, because really bright, and the envelope, the surface, maintain the original composition. After, in a giant branch, due to the drop caused by this thin shell instability, it's no, it's completely mixed. Their chemistry is not more a good indicator of the composition, common composition of the other stars.
Okay, thanks.
Not at all. This is really tricky because it's quite strange. It seems not because the other makes sense also in general due to the negative gravothermal heat capacity. The star is something strange. Usually, to compress a gas, you need to cool it spontaneously because you can compress and heat it, but you are doing the work on the gas. Here, it's the gas as doing himself a work inside. So all started to heat and expand on the other. In this case, the stars are on the opposite. When start to increase in temperature, it will compress. Essentially, because you need to compress to increase its temperature, which you are connected. So I have this strange secular, but at least is helpful. And we have the ladder thermal instability due to the degenerate gas. That, for example, for the helium, it goes well because the degeneracy is lifted off just in time. With the carbon, will be a little more detonation, that the detonation is. In fact, the increase in temperature is so high that start to go quickly toward all the other reaction quickly. And usually we see when stars, we have white dwarf of helium, degenerate helium, we can have white dwarf of degenerate carbon oxygen, usually 50-50. But we don't have degenerate white dwarf with other element because one we start to burn the carbon, the stars we go just up to the end. Doesn't the next then I manage to stop it because the thermonuclear runaway is so strong that arrives up to iron and they're stopped because it's a process that definitely absorbs energy and will block the runaway. But as we saw, is stop it too quickly. Yeah, here is just to say it's the situation and we saw that depends on the A, that is P, depends on with the density. That is actually what is the adiabatic coefficient. And we'll see exactly also in the dynamic instability or stability, it depends on the scene. Again, the adiabatic coefficient will be inside, and this also we see again that for the reason why we check how was changing the adiabatic coefficient during the ionization or with changing the weight of the radiative pressure over the total pressure. Here is seen it was the previous. Generally, the variation in density change completely with this case, but here since the the thin shell have a different variation among expansion and the density. React slightly different way at the change more because it's a thin shell really thin. X is definitely smaller than the radius, so this is definitely bigger, more than 3. So we have a strong variation with among radius and density. Any more question?
No.
Okay, we'll stop here and we'll see on Wednesday.
See you on
The
Wednesday.
exam I give to Ramon, and the first will be in 2 weeks, the 12th of June. My idea is giving you, now see on how much time, several questions, something to describe.